Hello, my name is B.S. Stella, and this is Group 16 from Group 16. We're taking you through the contrastive knowledge distillation, banana leaf disease diagnosis using sparse capsule networks. Other name is Banana Care. This is the pitching video. Well, here is the problem statement. A lot of Ugandans or people in Uganda, they eat, their staple food is banana, but these bananas suffer from some diseases, and this reduces the yields or losses. Yeah, for the problem here, we're specifically going to talk about two diseases. That is the bananas and wilt, and then the segatoka. For this bananas and wilt, it's a bacterial disease that causes premature fruit ripening, blackening, and eventually the plant's death. And then segatoka, it's a fungal disease. Then it also causes the banana leaves to become yellow, and eventually the plant dies as well. This leads to severe economic losses for farmers. And then the other challenge is that the traditional disease detection methods, such as the visual inspection and the lab tests, they're slow and labor intensive and often inaccurate. So that's why this brings a gap which needs to be filled, and with this video can be able to close that gap. That's why we need the AI solution. And then the objective of this is that we're going to develop an AI-powered system for banana disease diagnosis. We're going to use computer vision models to classify banana leaf diseases accurately, then provide real-time treatment recommendations, and also ensure accessibility to the rural farmers. Then the solution overview is that there's a multimodal AI model that combines deep learning for the image-based diagnosis, and then the NLG for the treatment recommendations. This natural language generator model, it generates real-time advisory text for the farmers, basing on the input then provide treatments and prevention strategies. The impact of this is that it will be faster, more accurate detection and making decisions for farmers. And then for the data used, we can see we have three classes, and that is the healthy, segatoka, and the xanthomonas. This classifies the leaves and the diseases, because the signs of the earliest signs of these diseases are detected in the leaves. So that's why we use images of the banana leaves to detect whether the plant is healthy, having segatoka, or then these are some of the models that we trained them, and they learned. First one is CNN, Invention V3, and the rest. But our best performing model was the MobileNet V2 model. Then this is how the system architecture is going to be. This just shows you how the system is going to work, where you take an image or a plant, put it in the system, it will be preprocessed, where the features will be extracted and classified. And the system will classify whether the leaf is healthy, having segatoka or xanthomonas. After classification, to be taken to the NLP, the natural language processing, where the text-based treatment recommendations will be provided, and the response will be generated by interface. And the implementation details, the language used, we have Python, and the frameworks, TensorFlow, PyTorch, OpenCV, and all these are for image processing. In the platforms, we used Google Column for training our models. Then for the deployment, some of the tools that we use, Flask API, and then Streamlit for the UI generation. These are the results and the evaluation. This is just a graph showing our best performing model, and that's the mobile net V2 model. This is the accuracy graph, and this is the confusion matrix. This shows the number of images that are classified correctly as well, and this shows the number of leaves of images that were classified correctly as in class Segatoka, and most of the images were classified correctly under the class one as compared to the other classes. So I had my group to take it. Thank you.
Hi everyone. So we are going to continue with our presentation and we are going to look at the impact and relevance of our project to Ugandans and to the agriculture sector. So we know matoke is a staple food and a key source of income for many Ugandan farmers, both small scale and large scale farmers. But most times banana wilt, as well as segatoka and other banana leaf diseases, threaten these crops. And in turn, they threaten food security and farmer livelihoods because they depend on these plants for survival. Some of our target users are small-scale banana farmers, cooperatives, and agribusinesses that operate on a large scale, as well as non-government organizations that create the agriculture regulations. So our project aligns with the SDGs 1, 2, 3, 9, and 13, which are no poverty, zero hunger, good health and well-being, industry and innovation, and infrastructure, and climate change, respectively. And we can see in all these SDGs, the ultimate goal is to protect farmers from crop losses, to protect banana yields and ensure food security, and as well as utilizing AI and machine learning in our project to detect these diseases earlier. So moving on, some of the intellectual properties that we identified for our project include the computer vision model, which is used for the banana leaf disease classification. Then we also have the AI disease advisory system, custom data sets, and the images we collect can be copyrighted if we are to collect any banana leaf images for classification. Then the software powering the diagnosis system is also one of the intellectual properties, as well as the product name, Banana Care. Then monetization and scaling, how we plan to monetize our project. We plan to have a subscription-based model for farm cooperatives and agribusinesses where they'll be paying per month according to the features that they want to be able to access. Then we also have the pay-per-use model where farmers will pay for each diagnosis, each image that they put into the system. They will have to pay for that diagnosis. Then we also have the NGO-funded projects, as well as also licensing our API to agri-tech companies that might want to use it. So as we scale our project, we did a SWOT analysis, and these are some of the strengths and weaknesses, opportunities, and threats. So some of the strengths, it's cost-effective for farmers, recommendations are data-driven, and there's automated and continuous learning because the model learns from new data. Then some of the weaknesses, there's limited data set availability, the fact that we need internet, there's internet dependency, and some of these rural areas don't have internet. Then farmer training is required, as well as good image quality, which is also required in order to classify the banana leaf diseases accurately. Then some of the opportunities include expanding to other banana leaf diseases such as fusarium wilt and also other crops, other common food crops. Then there's also commercialization and agri-tech startups and farmer advisory and extension services. Then some of the threats are competing technologies, regulatory barriers, climate change, adoption resistance, and cybersecurity and data privacy risks because we are going to be handling a large amount of data from different users, those other farmers. So our system demonstration, this is a screenshot from Streamlit, which is an interface, which provides an interface in which our model sits, and we're able to access it through the Flask API. So when I browse a file here, I'm going to drag and drop any file of any banana leaf image, and in turn here, the model is going to classify it according to the disease it has, or whether it's healthy, or whether it has early symptoms of either Sigatoka disease or Xanthomonas. And the prediction is shown as here. So when we put in this image, it was predicted as a Xanthomonas image, meaning that this banana plant has bacterial wilt. So these are team contributions. Myself, I worked on exploratory data analysis, model training and evaluation, the concept paper, the business model canvas, and my colleague works also on model training, model deployment, implementation of explainable AI techniques to the models, and also the concept paper. So some of the lessons and challenges, I'm going to start with the challenges. There's complexity during model training, computational resources like training time, and also bias in the chosen data set because we have the Xanthomonas class having very many more images than the other two classes. So when we put in an image, the model is biased and lies more towards the Xanthomonas class. Then teamwork challenges, there's time constraints as well as remote collaboration issues because we're using Google Colab. Then teamwork and process improvements. There's improvement in collaboration and adaptability in problem solving. Some of our future works, we hope to enhance the accuracy of the model and real-time processing. And we also hope to expand dataset diversity so that we have each class having equal number of images to the other class such that the model is not biased. Then some of our scaling plans, we hope to apply AI to detect other banana leaf diseases, extending mobile app usability, expanding the dataset, and optimizing the models for edge devices. So to conclude, we have seen the effectiveness of deep learning models in the ability to learn complex patterns and features from images because we trained about 5 deep learning models, including some pre-trained models. Then we also saw the importance of dataset quality, class balancing, and sample size, such that the dataset is not biased. We know that we have to ensure that the classes are balanced. And yeah, then we also faced some computational challenges whereby we had to use a lot of memory during the training of the model. Then we also see potential for real-world deployment, and this will require us to address computational and scalability challenges. Yeah, thank you.